All right, let's talk about a fundamental law of physics that you're actually using every single day, probably without even realizing it. It's called Boyle's law, and it's all about the relationship between the space a gas takes up and how hard it pushes back.
Have you ever really thought about this? When you squeeze a balloon, the more you shrink it, the harder it seems to push against your hands. That simple feeling, well, that's the key to understanding a really powerful scientific idea, the link between pressure and volume. So, let's get into it.
To really get the law, first we need to understand the man who came up with it, Robert Boyle. Because his discovery wasn't just about one little experiment, it was part of a whole new revolutionary way of thinking about science itself.
You see, before the 1600s, science was basically a thinking game. If you wanted to prove something, you'd use pure logic or just quote what some famous dead guy once said. But then, in 1662, Robert Boyle came along with this radical new idea. If you have a question, don't just sit and think about it. Go build an experiment and force the universe to give you an answer.
And using his famous vacuum pump, he wasn't just guessing about things. He was proving stuff we think is super obvious today, like the fact that sound can't travel in a vacuum because there's nothing there for it to move through, or that a flame needs air to burn. He was literally building the foundation of modern science one test at a time.
And one of his most famous experiments led him right to solving what we can call the pressure-volume puzzle. He started noticing this really clear pattern whenever he took a bit of air, trapped it, and then started to squeeze it.
The pattern he found is called an inverse relationship. Now, that sounds kind of technical, right? But it's actually as simple as a seesaw. When one side goes up, the other side has to go down. That's really all it is.
And this is exactly what Boyle figured out was happening with air. If you increase the volume, give the gas more room to spread out, the pressure it creates goes down. But if you decrease the volume, cramming it into a smaller space, that pressure goes way, way up. Exactly like our balloon.
So this observation became his famous law. What it means in math terms is if you multiply the pressure of a gas by its volume, you pretty much always get the same number, a constant. But, and this is a really, really important detail, this only works if you keep the temperature exactly the same.
Okay, so we know what happens, but why? Why does squeezing a gas make its pressure shoot up? Boyle himself couldn't quite explain it, but today we can, and it all comes down to this kind of frantic dance of tiny, invisible molecules. The explanation for all this comes from something called the kinetic molecular theory. The main idea here is that any gas, like the air all around us right now, is just a giant swarm of countless tiny particles just zooming around in straight lines until they smack into something. So just imagine these little particles bouncing around in a big box. They've got plenty of space to travel. Now, what we feel as pressure is really just the combined force of all those particles hitting the walls of the container. With all that room, they don't hit the walls very often, which means you get lower pressure.
But now, what happens if we take that same number of particles and we cram them into a tiny little container? All of a sudden, they're super crowded. They can't travel far at all before they slam into a wall. So more collisions every second means more force, and that means much higher pressure. It's like a microscopic traffic jam.
Now, this theory is great and all, but remember, Boyle's golden rule, you have to test it. And we can actually do a modern version of his experiment right now and see the data with our own eyes.
So here's how you do it. You just trap a little bit of air in a regular syringe, hook that up to a digital pressure sensor, and then you just push or pull the plunger to different volumes and write down the pressure reading each time. It's a really elegant, simple way to see the law in action.
And what does that data tell us? Well, let's say at 20 milliliters of volume, the pressure is 760 units. But look what happens when we cut that volume exactly in half to 10 milliliters. The pressure exactly doubles to 1520. Cut the volume in half again to 5, and what do you know? The pressure doubles again. The pattern is just crystal clear.
So how do we actually prove this with the math? Well, if you try dividing the pressure by the volume, the numbers you get are all over the place. There's no pattern. But if you multiply the pressure times the volume for each measurement, you get a nearly constant number every single time. And that is the proof. The relationship is definitely inverse. Okay, so this might seem like just a cool little experiment for the lab, but the truth is, this 350-year-old law is happening all around you and even inside of you every single second of every day.
Go on. Take a deep breath. Right now, your diaphragm just moved, which increased the volume of your lungs. That simple action decreased the pressure inside your chest, and the higher pressure air from the outside rushed in. That's Boyle's law. It's also why scuba divers have to come up to the surface slowly,
and it's the principle behind how a syringe works. It is absolutely everywhere.
So, we've seen how pressure and volume have this perfect little inverse dance. But remember that one super important rule. The temperature has to stay the same for it to work. So the final question I want to leave you with is this. What do you think happens to that dance when you start to turn up the heat? That's a puzzle for another time.